Welcome back to a course on complex analysis. We have been discussing about the concept of antiderivatives. So, when we started this concept, I just stated the theorem which states that suppose a function is continuous on a given domain D, then if one of the following statements is true, then so are the others. Which means we are not saying these has to be true always. If suppose if a function has an antiderivative throughout the domain, then the integral over any closed contour will have the integral value to be 0. This will imply that, and that will imply integral z1 to z2 f of z dz would be the antiderivative. Here your big F is the antiderivative which is evaluated at the point z2 minus evaluated at the point z1. This value is going to be like this, right? So with these ideology, okay, we have not proved the theorem formally yet. Actually, that is the agenda for this lecture. With the help of these theorem, we have worked out few problems to understand what is the purpose of the theorem. Okay, so that we have done in the previous lectures itself. Now let us formally start proving the theorem. Okay, so let me start. So first, let us assume that statement A is true. What is that? F of z has an antiderivative throughout D. So if it possesses an antiderivative, what does this mean? Which means when you suppose if I take big F of z to be the antiderivative, when I differentiate this one, I would get F of z. Okay, this is the meaning of an antiderivative that you all know very well, right? So antiderivative d, let me say that as big F of z. Okay, now what should we prove? We will have to prove the second thing is true, that is the integrals of F of z along contours lying entirely in D and are in simple. Why should I write all these things that are trivial from the statement itself? You can refer the statement. So let me just write down the ultimate thing that we have to prove, that is integral z1 to z2 f of z dz is big F of z2 minus f of z1. So this is happening to be true. This is what we'll have to prove. Okay, so which means, this means what? The integration is independent of the path. So on which path we are integrating, that doesn't matter. Okay, so only the endpoints matters. That is what we'll have to prove. Okay, now in order to prove this, let me consider f a contour C, which is from the point z1 to z2, is a smooth arc lying in the domain D. Okay, if it is a smooth arc, then what is going to happen? Then we have already proved a result that tells us that, sorry, the derivative of the function z of t is nothing but f prime of z of t multiplied with z prime of t. So this is nothing but big F is what? Which is an antiderivative of small f of z, right? So this simply becomes f of z of t, z prime of t with, okay, if we say which is a smooth arc, okay, then of course this is going to happen. Okay, now we have proved very well that the fundamental theorem of calculus can be extended to the complex valued functions, right, for intervals of this type. So that is by the extension of fundamental theorem of calculus to the complex valued functions, we get integral over c f of z dz may be written as integral a to b f of z of t multiplied with z prime of t dt. So this is simply f of z of t over the limit a to b. So this would give you f of z of b minus f of z of a. Okay, here what is z of b and z of a? We don't know what this b is, but we know this is the second endpoint. So this is z2, and your z of a is z1. Then, okay, since this is happening, what do we get? We get integral over c f of z dz is f of z2 minus f of z1. Okay, so I mark this as equation 1. This is the requirement, right? So we have proved this happens to be true for simple arcs, sorry, smooth arcs, right? So the claim is proved for smooth arcs. Okay, now we'll have to do few more things. What? We'll have to prove, or we are just going to claim equation 1 is true for any contour C. Okay, so any contour C which lies in D. So inside the domain only we are talking. We are not going away from the domain. Inside the domain we are going to identify a contour which can be any contour in general. Okay, so by any contour what do we mean? So by the definition of a contour, by the definition of a contour, C consists of finite number of smooth arcs. Let me name them as Ck with k running from 1 to n. Okay, and each Ck extending from Zk to a point Zk plus 1. From Zk to Zk plus 1 it is moving. So then by the previous arguments. Integral over ck f of z dz is what? Big F of zk plus 1 minus f of zk. This is true for k running from 1 to n. Okay, and here your z1 remains z1 itself, and your zkn plus 1 is going to be your z2. Okay, in the general context we have those two things, right? So that is happening to be like this. Okay, uh, now what is going to happen with integral over c f of z dz? Since c is the what, c consists of the finite number of smooth arcs, this splits into integral over c1 f of z dz plus integral over c2 f of z dz. It goes till integral over ck f of z dz. So this is by the properties of contour integrals. Okay, I'm not using anything new or something like this. So this is just a direct result from the properties. So and this is what? This is f of z2 minus f of z1 plus this is f of z3 minus f of z2. It goes this way till cn we have, right? So what is the term we would get for cn? It is zn plus 1 minus f of zn. In the previous thing we would have f of zn minus f of zn minus 1. If you see, your terms like this gets cancelled. Okay, so this also gets cancelled, this also gets cancelled, and we are left with only f of zn plus 1 minus f of z1. Notice that here c extends from z1 to zn plus 1. Therefore, integral over c f of c dz is f of zn plus 1 minus f of z1. Hence, uh, instead of writing this integrals, I may write equation 1 is true for all contours. Okay, now we shall assume integral over c f of c dz is f of z2 minus f of z1. So this is happening. Okay, where c extends from z1 to z2. So we have this, right? Now what is our claim, or what are we trying to prove? We are trying to prove integral over c f of z dz is 0 for any closed contour. Okay, so for this you can consider the thing. Okay, supposing you have this and you have some domain like this. Okay, so inside the domain you have the point z1, you have the point z2. You don't know what the contour is. Okay, so you may have something like this. Okay, let me mark this as C1. Let me consider this as C1. Okay, and something like this. Let me take this as C2. Both has to come from Z1 to Z2. Okay, both should start at Z1 and end at Z2. I am taking this way, right? So by taking this way, what am I going to do? Let us see now. Okay, so in order to prove this, we let Z1 and Z2 denote any 2 points precisely on any closed contour lying in D and form two paths C1 and C2. Okay, so how should these paths be? Each with initial point Z1 and final point Z2 such that the entire C is C1 minus C2. Okay, so by our assumption, what the integration is independent of the path, right? So what was our assumption? Integration is independent of the path. So we shall write integral over C1 f of z dz is same as that of integral over C2 f of z dz. Even though these two are two different paths, integration is independent of the path. And since the initial point and the final points are same, we have these two integrals to be equal, right? So what can I say more about it? So I can also say integral over C1 f of z dz, and instead of integrating it in C2, let me take it in the negative direction. But still I wish to hold this quantity to be equal. So what do I do? I just negate this in value. So this gives me integral over C1 f of z dz plus integral over minus C2 f of z dz, which is happening to be 0. And this very well concludes integral over C1 minus C2 f of z dz is 0. That is integral over C f of z dz is 0. Okay, so this one we just wrote by the property of contour integrals. Okay, so I think we have proved what we were supposed to prove. Okay, now let us make the next supposition. Assume integral over c f of z dz is 0 for any closed contour C in D. So with which what should we prove? We will have to prove f of z has an antiderivative, we call that as big F of z in D. Okay, that means which completely lies inside D. This is what we'll have to prove. So what are we going to do? Okay, so now we'll assume that the values of such integrals are in fact 0. Yes, that is the thing we have assumed. And we start by showing that the integration is independent of the path in D. Okay, actually what we have done, we are going to assume the values of integrals are in fact 0. So this is our assumption with which we start showing that the integration is independent of the path in D. So hope you are getting what I'm trying to say. Let me write that down. So assuming that the values of integrals. So what kind of integrals? Integrals around closed contours are 0. We start by showing the integration is independent of the path in D. Okay, for which we let C1 and C2 be any two contours lying in D from a point Z1 to Z2, and observe that since integrals around closed contours are closed paths lying in D have value 0, that is the equation. I think I'll have to do it in different color. So that is the equation. What equation? So integral over C1 f of z dz plus integral over minus C2 f of z dz is 0. So this holds. Okay. So with which what we are going to do? If this holds, that implies integral over c f of z dz is 0. Since the integration is independent of the path, we define big F of z to be some function which is from z0 to z f of s ds. Okay, since it is happening to be true, we define big F of z in this form inside the domain D. Okay, so now the proof of the theorem is complete when we claim this big F prime of z is small f of z. So for which what are we going to do? Let us see. z plus delta z be any point distinct from z and lying in some neighborhood of z. Okay, so now we consider f of z plus delta z minus f of z is nothing but integral z naught to z plus delta z f of s ds minus integral z naught to z f of s ds. So if you just see what you can write about these things. So I shall have this as integral z naught to z plus delta z f of s ds and plus integral z to z naught f of s ds. Again using the properties of contour integration or usual integration. So this turns to be integral z to z plus delta z f of s ds. So I get this one. Okay, where the paths of integration may be, so this is very important, right? So may be selected as a line segment. Okay, now what is integral z to z plus delta z ds? This is simply s, substituting this limits. So you will get z plus delta z minus z, which is simply minus, sorry, delta z itself, right? So from which we can write f of z equals 1 upon delta z integral z to z plus delta z f of s ds. This is what? This is the mean value theorem for integration, right? So with which we write this one. So therefore f of z plus delta z minus f of z upon delta z is nothing but, okay, from which I subtract this quantity f of z, which is 1 upon, okay, so I'll have to write things out, right? So it is 1 upon delta z. So this quantity, this is what? Integral z naught to z plus delta z f of s ds and minus, I think here, so if I'm not wrong, this is going to be here, yeah. So this is gonna be here minus integral, so first of all 1 upon delta z integral z to z plus delta z. Okay, so here also z to z plus delta z f of s ds, here we would have f of z ds. So this is when you take these things as common and the integral limit is also common, so this is what you are going to have, f of s minus f of z delta z, sorry, not delta z, it is simply delta s, right? Now using the fact that f is continuous at that point z, hence for each positive number epsilon there exists a delta positive such that absolute of f of s minus f of c, which is smaller than epsilon, whenever absolute of s minus c is smaller than delta. Okay, so this tells you what your absolute of s minus z is going to be very small quantity. Okay, so when that is a very small quantity, of course the corresponding values of the function is also lying in the difference of very small quantity, right? So now let us proceed with the proof. Consequently, if the point z plus delta z is close enough to z so that your absolute of delta z is less than delta, then we can say absolute of big f of z plus delta z minus f of z upon delta z minus f of z, which is smaller than 1 upon absolute of delta z multiplied with what? Absolute of f of s minus f of z, which is less than epsilon, and absolute of delta z, which happens to be epsilon. Okay, this happens to be less than, yeah, actually it is epsilon. So from which what we conclude is that this quantity is less than epsilon whenever absolute of s minus z is smaller than delta. So this implies limit delta z approaches 0, f of z plus delta z minus f of z upon delta z, sorry, big F here, right? So which happens to be small f of z, or we can say big F of z prime is small f of z, and with which we have come to the end of this theorem, and with this we shall conclude this lecture as well. So if you get any doubts, you can post it in the comment section, or you can write to me in my mail. So thank you.